Okay, let's go over some SIMD examples together. First, let's go over this add no SSE function. It takes 3 arguments, size, and 2 array pointers. So what it does is that it will iterate through each array to add each pair of elements together, then assign the value back to first array. So this is the same function with SIMD implementation. Because we're using SI128, it means we're operating on 4 integers at a time. The counter for iteration will be incremented by 4, and the stopping condition will also need to change. We'll need to stop 4 elements before the size. So this for loop condition only works if size is a multiple of 4, but if size is not divisible of 4, the AND condition will need to change. We need to find the biggest number that's multiples of 4, but smaller than size. And we also need to add another small for loop to deal with the leftover values. For that for loop, the start value of I is the end value here. And then we need to iterate through each leftover values and do the operation there. The tail case implementation is not present in this lecture slides, so I highly recommend you to look at the discussion worksheet. It will be really helpful. There are a lot of good practices, and I strongly recommend you to do that before lab, because it will save you a lot of time and frustration. SIMD functions are really weird and hard to learn in the beginning. It does take some time to make yourself comfortable with the syntax and format. Discussion worksheet is a very good place to start. Alright, move on. We'll need to use this load function to load the first 4 elements in the array to a vector. The argument is a pointer. The value equals the address of the first element of the array. Then we name the return the 128-bit vector first values. We want to do the same thing for the second array. Load the value from first 4 elements in the second array into this 128-bit vector called second values. And then we can use this add SIMD function. Quick reminder, EPI32 means extended packed integers. Right? So you will treat these 2 arguments as a pack of 4 32-bit integers. By calling this function, we're adding each pair of 32-bit integers from these 2 vectors and store the value to first values vector. After we are done with the calculation, we want to store it back to the array. For the storeU function, the first argument is the pointer, which equals the address of the first array. The second argument is a vector that we just calculated first values. Right. After this iteration is done, we're moving on to I equals 4, the next 4 elements in the array. We were dealing with integers. You can also do this with floating point numbers. The mark will change from SI128, EPI32 to PD or SD. Packed double or scalar double. So for packed double, for a 108-bit vector, the operation will be executed to each double. For scalar double, the operation will be only applied to the double located at the lower bits, and the double located at higher bits will remain the same. You just need to kind of be careful with the 2 different marking. It means totally different things. Alright, so this example is about matrix multiplication. I know you've been dealing with that a lot in project 2, but unfortunately you will need to deal with it again in project 4. And if we're going into the machine learning field, everything is just matrix multiplication. However, matrix multiplication is a very good place to implement SIMD. And we will be going over this tiny example 2x2 matrix multiplication here. We have matrix A, matrix B, matrix C. All of them are 2x2 matrix. For the format, Cij, I means row, J means column. So A11 means first row, first column. A21 means second row, first column. And this is a mathematical formula for how we get C11, C12, C21, C22. C11 equal A11, B11 plus A12, B21. So in order to calculate C11, we're multiplying the first row of A and the first column of B, right? For C12, it's just first row of A and second column of B. Same for C21 and C22. Just by looking at this, do you realize something? We're doing a multiplication, then addition. For all 4 elements of C, we're doing the same operation on multiple data. SIMD, single instruction multiple data. here we go, good place to do SIMD. But how can we do that? Okay, let's try to find some pattern here. We're storing the array here in column major. So A11, A21 will be sitting together. A12 and A22 will be sitting together. Okay. Since it's column major, let's look at the column and trying to find some pattern there. Okay, so for first column of C, for the multiplication, it's A11 times B11, A21 times A11. A11, A21, wow, it all belongs to the same column. What if we just load the column of A into a vector, make a vector contains copy of B11, and multiply them together using a SIMD function? That seems to work, right? So for the second column of C, it's a similar thing. A11, A21, first column of A, B12, B12. We can make a new vector out of it, right? And these two multiplications seems like they can be executed at the same time as well. And for the second pair of multiplication, it's exactly the same thing. We just switch from the first column of A to the second column of A, from the first row of B to the second row of B. So the operations in the red boxes and purple boxes can be done in one iteration. And for the second iteration, we're going to do the multiplication for the rest 4. After that, we can just add them together using SIMD function as well. Let's break it down into multiple steps. So the array here is saved in a column major. So C1 means the first column, C2 means the second column, A indicating the column of A. So right here we're doing A1i, A2i. When I is 1 is the first column of A, when I is 2 is the second column of A. B1, B2 here will have a different meaning. Let's see. So C1, C2 are all initialized to 0 in the very beginning. At the first iteration, we're looking at the first column of A and the first row of B. We can use this function mmloadPD to load the two doubles from A into a vector. And then we can use mmload1PD to load the value of B11 and store it in the high and low double words in the vector. Similarly for B2, load the value of B12 and store it both in the high and the low double words of the vector. Now we're all set up. Right. Let's look back to the formula again. So for the first column of C, we need to do A11 times B11, A21 times B11. That can be accomplished by multiply vector A with vector B1, mmulpd AB1. For the second column C, similarly, A11 B12, A21 B12 can be accomplished by multiply A with B2, mmulpd AB2. That's the first iteration. In the second iteration, we'll need to calculate the 0 part. So when I is equal to 2, we're looking at the second column of A, A12, A22, the second row of B, B21, B21, B22, and B22. Same operation. Multiply A with B1 give us second part of first column of C1. Multiply A with B2 give us the second part of C2. We can call addPD to add two multiplication together. That gives us the correct value, the first column of C and the second column of C. The final step is just store the vector we just calculated back to the array. So this is how it actually looks like in C code. So ABC, 3 matrix, contains 4 doubles. I have 2 local variables. LDA will be used to calculate the new address of the pointer, and I is our iteration counter. Then we declare a couple 128-bit vector C1, C2, A, B1, B2. We first initialize A, initialize B, initialize C. Then we want to load the first column of C into C1. The pointer address is just the beginning of the array C. And then we want to load the second column C as well by doing the same thing, mmloadPD C plus 1 times IDA. LDA equal 2 because the second column C is starting from the third element in the array. Then we go into the for loop, only need 2 iterations. Inside each iteration, we want to load one column of A. So the first one will be the first column, I equals 0. So now this 128-bit vector A contains 2 doubles from the first column of A. Then we construct vector B1 contains 2 doubles from B11 from the very first element of B. Just a reminder, load1PD will basically make a copy of the value from that address. And for B2, similarly, it's a vector contains 2 B2 too. So if I equals 0 here, it points to the second element in the array. If I equal 1, it points to the fourth element in the array. With all the vectors ready, then it comes to the operation. By multiply A with B1, we calculate the first part of multiplication with first column. Adding that with C1, C1 initialized is just 0, and then update the value of C1. Then we do multiplication on A and B2, give us the first part of multiplication for the second column C. Right. Similarly, we add that with C2 and then update C2. Okay, this is the first iteration. After that, we'll get to the second iteration where we're basically multiplying the second column of A with the second row of B. Then add the second part of multiplication with the updated values of C columns. And then after 2 iterations done, we can store back C1, C2 into array C. First argument is the address of the pointer. The second argument is the actual vector, and we're using store PD for that. So we just went through a very detailed steps of how to do SIMD on a 2 times 2 matrix multiplication. But when you're dealing with project 4, the size of matrix will be replaced by a variable. So you need to reconsider the iteration counter, the end condition for the iteration counter, the address of the pointer that you want to pass into each intrinsic function, also the number of times you need to do multiplication and addition. So hopefully this workthrough can provide you some direction about how to approach this kind of problem and what you need to think about when you're trying to parallelize your code. And I encourage you to think about what is a generalized way of doing matrix multiplication.